Welcome to my channel Fee Concepts CHM. This is the third part of the series of OPAMP applications. In the last two videos we have seen some of the applications of OPAMP. Now we will see some more applications. One is ASTABLE multivibrator using OPAMP. With positive feedback, it is possible to build oscillator circuits to generate an output with no external input. So we'll see about a relaxation oscillator, ASTABLE multivibrator, or this circuit is also called as a relaxation oscillator. So in this figure, we can see that there is no external input applied. The circuit produces a rectangular output which swings between minus Vsat and plus Vsat. Assume that the output is in the positive saturation. Because of the feedback resistor R, the capacitor will charge exponentially towards plus Vsat. But the capacitor voltage will never reach plus Vsat because the voltage crosses the UTP, which you can understand from this waveform. The capacitor is charging when the output is at plus Vsat. So it charges and goes towards plus Vsat, but it doesn't reach there. As soon as it crosses UTP, the output will switch from plus Vsat to minus Vsat. With the output now in the negative saturation, now the capacitor will discharge. The capacitor voltage will cross through 0. It will go towards minus Vsat. But as soon as it crosses the LTP, the output, which was now minus Vsat, it will switch to plus Vsat. The cycle then repeats. Because of the continuous charging and discharging of the capacitor, the output is a rectangular wave with a duty cycle of 50%. That is, the on time and the off time, they are equal. By analyzing the exponential charge and discharge of the capacitor, we can derive the formula for the period of the output. That is, T is equal to 2RC into ln of 1 plus B upon 1 minus B, where B is the feedback fraction, which is given by B is equal to R1 upon R1 plus R2. Now this circuit is called as a relaxation oscillator because it generates an output signal whose frequency depends on the charging of the capacitor. If we increase the RC time constant, it will take longer for the capacitor voltage to reach the trip points. Therefore, the frequency is lower because the time periods become large. So, the frequency decreases. Square wave and triangular wave generator using OPAMP. By cascading the relaxation oscillator and an integrator, we get a circuit that produces a triangular output. The rectangular wave of the relaxation oscillator is given to the input of the integrator, which will then produce a triangular output. The rectangular wave, as we had seen earlier in a relaxation oscillator, it swings between plus Vsat and minus Vsat. The period can be calculated using this formula of T is equal to 2R3C1 into ln 1 plus B upon 1 minus B. B is the feedback fraction. The triangular wave has the same period and the frequency. Now we will see another triangular generator. Here, the output of the non-inverting Schmidt trigger, this is a non-inverting Schmidt trigger, its output is a rectangular wave. This also we had seen in the earlier video. And this rectangular wave is now the input to the integrator. And the output of the integrator is a triangular wave. The triangular wave you can see is again fed back, which drives the Schmidt trigger. So here the first stage drives the second and the second stage drives the first one. Figure B is the transfer characteristic of Schmidt trigger. When the output is low, the input must increase to UTP so that this low output will switch to now a high output. Likewise, when the output is high, to change the state, the input must decrease. It should go below LTP so that this output will switch back to the low state. When the Schmidt trigger output is low in this diagram, the integrator produces a positive ramp which increases until it reaches the UTP. Now at this point the output of the Schmidt trigger switches to the high state and the triangular wave reverses its direction. The negative ramp then decreases until it reaches the LTP, where another Schmidt trigger output change takes place, that is, it goes from the high state to low state. So in figure C, the peak to peak value of the triangular wave equals the difference between the UTP and the LTP. Thank you for watching this video.